So Alex, after the greetings yesterday, I could not possibly say anything that compares, but just thank you for everything that you do and did and you are, and just really thanks. And okay, so actually I made a presentation about expanders because this is an expander seminars, but then I talked to Alex and he asked why instead don't you talk about your last result with Noam? So I will talk about the last result with Noam. So Noam is Noam Tashmahir, and the result is about independent words in the free group, and they may be surprising, maybe not, claim that they're really separated. So let's see what it means. So our setting is as follows. We have a free group F, and I say that it is finitely generated. We have a word and a finite group G. Okay, I try to stay with these notations. And the setting that maybe one can say most famous result that studied this the setting of drawing a random homomorphism is maybe Puder Parzanchevski, and I will get to it right away. So the idea is that for every single letter in the free group, you take a uniformly random element of the finite group G independently of the others and substitute it in the letter. Now every word becomes a random variable in G. And its distribution is called the word measure. Is a very studied concept. Now an equivalent way of saying all this is that since the set of homomorphism from the free group to a finite group is just the set is canonically isomorphic to the set of just marks from the letters to G, one can say that all we did here is just drawing a random homomorphism from the free group to the finite group out of the finitely many options and substitute W. So for example, if we started with say the commutator of two letters, then the random variable that we get in finite group G is just the commutator of the two random elements. Now let us have a very easy observation. So if we started with two words, W1 and W2, and applied a random homomorphism alpha, then if W1 and W2 didn't have any letter in common, then surely we get independent random variables because each letter is independent of the others, right? So here's a maybe natural question to ask. Suppose every finite group G sees just two independent random variables. Does it mean that the two words W1 and W2 that we started with shared no letter? So naively, no. This does not follow. For example, let us take. Oh no, this is not the right presentation. Someone of the organizers. I sent a new version some days ago.
Okay. To me?
To all the organizers and Kasai. Okay, I'll
check in the Kasai email and send it.
So I'll proceed without the presentation for some minutes. In the same mail that I sent the title and abstract? Yes, this mail exactly.
Okay.
This one. Okay, thank you.
Basically, the question of whether two words share a letter or not depends on the basis you choose for the free group.
Exactly. So let's say an example. Say every finite group we get independent random variables because actually F is also the free group on A and AB. So if you write it in this basis, then surely they share no letter. And this is a general phenomenon because if we take an automorphism of the free group, then it acts on the set of homomorphisms from the free group to the finite group G via composition. Okay, so alpha goes to phi composed with alpha, and or maybe the other way around, or just let's say that the composition is from left to right. Oh, thank you very much. Great. So this is just a finite set permuted by phi, so it preserves the uniform distribution, and therefore if we change the basis of the free group, or equivalently apply an automorphism of the free group, then we still have the same distribution on any finite group. There's still the same joint distribution of W1 and W2 on any finite group, and in particular they stay independent. So maybe the next question to ask is, suppose that for every finite group G we have W1 and W2 induce two independent random variables. Does it mean that for some basis one can write the words with disjoint letter? And our main result is that yes. So let us say that the two words W1 and W2 are freely separated if in some basis of the free group they share no letters. Or in another form, one can split the free group into the free product of two free groups such that each word lies in different components. And then the theorem is just that this is if and only if. And of course one direction that if they share no letters in some basis then they're independent is the easy one. Apparently for the other direction it suffices to test the finite groups, symmetric groups, Sn. So it turns out that one can say a lot more about what happens here. So let us denote by correlation, the unnormalized correlation of two events in a probability space. Just the probability of the intersection minus the product of the probabilities. Or equivalently, this is the covariance of the indicators. And for the two words W1 and W2 in the free group, let us denote by A the event that the word fixes the point n, or equivalently lies in the copy of Sn-1, the symmetric group on n-1 element that lies inside Sn. So all the following are equivalent, and all the implications 1 to 2 to 3 to 4 will be the easy ones. So W1 and W2 are freely separated. The images under random homomorphism to a finite group are independent for every finite group. 3, the correlation, if you study specifically the symmetric group, and you study specifically these events, then these events are uncorrelated for all n. And the last condition is that for infinitely many n, the correlation is non-positive. These are all equivalent. So stating it another way, the result also says that the correlation of these two events is always positive if you look at large enough n and you started with two words that are not really separated. And I want to emphasize that this is not just because two words are always positively correlated. I mean, maybe it's intuitive because if like the word has no constant, so if one word fixes a point, maybe I should expect that the permutations in the letters fixes this point, and then maybe it should increase the probability that the other word fixes this point. But this is actually true only for large n. So, for example, if you take, say, just the simplest example of x squared and x cubed, okay, just one letter, here now the letters in the three groups are x and y and not a and b. This is a completely new version of the presentation. The probability of each of them fixing the point 3 hydron in the symmetric group on 3 elements is 2 over 3. But if you look at the intersection, which is just the probability of a random permutation, just sigma itself to fix the point 3, this is 1 over 3. And so you can see that the correlation is actually negative. So it turns out that this non-negativity or positivity of the correlation is only asymptotic. In general, one has to take n quite bigger than the sum of the lengths, and in this specific example, for n equals 4, you get 0 correlation, and from 5 and so on, you get a positive correlation.
Quite larger, can we say a function, like a function of the sizes, in other words?
This, you mean?
Uh-huh.
I think 2 times the sum of the lengths should suffice, but
Not much larger, just,
yeah,
okay.
probably. I mean, this is just a rational function. I mean, whenever n is at least the sum of the lengths, then each probability is just concise with a rational function in n, and then we just analyze the leading term, and so moving from the leading term to whether the whole function is positive or not is just make n slightly larger.
So you have bounds on the coefficients.
What?
You can have bounds on the coefficients of this.
Yes. Maybe it should be much larger. I didn't check it, so I'm not sure. But
Okay.
I think it should work. Okay. So now let us give a much more precise and quantitative result, because until now we had this equivalence of qualitative results, and okay, maybe qualitative depends, because you see the equations and inequations, but now we'll have really a good understanding of what this unnormalized correlation is. So we said that two words are freely separated if there is some basis such that in this basis they share no letters at all. Oh, I just understood something. In the new version of the presentation, there was another slide at the beginning, and we completely missed it because we didn't use it.
That's okay.
So much troubles. So, okay. But anyway, we'll keep going. So given these two words, let us go over all subgroups of the free group that contains both words, and ask whether W1 and W2 are freely separated when considered in this subgroup. So it means that whether there exists some basis of J, the subgroup of F, such that the words are freely separated, like can written with disjoint letters, then take the minimum of all of these ranks. It turns out that these ranks are well defined, because a subgroup of the free group is still free. It's Nielsen Schreier, and it makes sense to look at to say that the minimum of the empty set is infinity. This will also be convenient in the letter formulas. And let us see some examples. So it turns out that if W1 and W2 are freely separated in F, then it is not quite trivial, but they are also freely separated in every subgroup of F. So it turns out that this quantity, which we call the separation rank, is infinity if and only if the words are freely separated in F. And on the other extreme, the minimum value of this invariant is 1, which measures precisely whether the words are just commute or equivalently are powers of a common root. In the free group, it's just the same. And generally, if it's not infinity, then it must get one of these values 1 up to the rank of F. So, for example, if the rank of F is 2, then, well, in this case, separation is not interesting, but we get that the values are 1, 2, and infinity. And also let us denote by a crit set of the two words, the set of subgroups J that appear in this definition and have the minimal rank. And it turns out that there is only a finite amount of them. This is very similar to a quite old theorem of Takahashi that said that for every given rank, the number of subgroups of this rank containing the specific word is just a finite set of subgroups. And then, using this invariance of the two words, we can give a quantitative statement about the correlation of the events of fixing. So maybe I should remind the definition of the events. So here the event AI is just fixing is just the event that our random homomorphism take the ith word, I is 1 or 2, into Sn minus 1, like fixing the point n. So the correlation, the unnormalized correlation, is just precisely this order of magnitude. So it is just n to the minus separation rank of the two words, with a leading coefficient that is just the number of critical subgroups, and there is also like a small error. And this form of theorem is very in the spirit of Puder Parzanchevski theorem that we will see more with more details later. And in particular, note that if n is large enough, then the leading term, well, it is a natural number and positive, unless the words are really separated, and so it is strictly positive for large n, and this gives us the equivalence of the four conditions that we've seen earlier. Let us see some examples. So if we start with, say, a square and a commutator, then one can compute the precise probabilities, 2 over n, 1 over n minus 1, and apparently the correlation is, the unnormalized correlation, is this rational number, rational function of n. And you can see that the leading coefficient is 1, and the degree is minus 2, so one can post priori deduce, but also compute explicitly that the separation rank of these two words is 2, and there is a unique critical subgroup, which in this case is just the group x to y, generated by x and y. Of course, this always works if the separation rank equals the rank of the free group, the ambient free group, then of course the free group will be critical. And in general, as we've said, this is always coincides for n large with the rational function of n. As another example, let us take the commutator of x and y and the commutator of x and z. Then both probabilities are 1 over n minus 1, and one can compute the unnormalized correlation. Now we see that the degree of this function is minus 3, so the separation rank of these two words is 3, and you can see that the leading coefficient is 2. So there are two critical subgroups that non-separate these two words. One of them is, as before, just the ambient free group X, Y, and Z, but also we have here the free subgroup generated by X, Y, Z inverse, and Y, X, Y inverse, and one can also look at this more geometrically, and say this is our base point. So actually we are looking at the fundamental group of this graph, which is F3, but with a specific map to the free group on X, Y, and Z, and one can read from this point the commutator of X and Y and the commutator of X and Z, and it turns out that in every basis of this free subgroup, the two words cannot be separated. And there are no more examples with this rank. Okay, so maybe questions until here, because until when can I speak? Now,
You have time. Like, we start 5 minutes later and it's like 40 minutes in total, so like you can go until 45, but stop 5 minutes before for questions.
okay, thanks.
Critical subgroups, non-separating subgroups think contain each other because you said they're minimal. In this example, one of them contains the other.
I don't have reason to. Just the rank is minimal. In the free group, okay, maybe, yes, this is a property of the free group that is very, maybe uneasy to get when seeing it, because it is highly non-notarial in the sense that it has, like, a non-abelian free group can have any rank subgroup.
You just said that the definition of critical non-separating subgroup was that it's non-separating and minimal among non-separating? Or is it
Minimal rank by inclusion, that's all.
Yeah, you,
oh, minimal rank.
yes.
Oh, I see, okay.
Yeah, sorry, when I said minimizing.
Minimizing is misleading here, because
Yeah.
it's not by
Yes.
inclusion.
Yeah, they minimize this specifically. Yeah, thank you.
Okay.
Thank you.
Do you
Really,
have an algorithm to find basis for this finite set?
Yeah, so actually there is if you just want to get the whether the two words are freely separated or not, then you can have a polynomial time algorithm, polynomial in the length of the words and the number of letters and everything. If you want to know more stuff, then maybe like exactly what is the separation rank and what are the critical subgroups, maybe you have to have like the length of the words to the power of the number of letters, or something which is can grow more than polynomial depending on your parameters. And
But it's all of this is fully algorithmic.
well, there are algorithms.
Yes.
One already implied them in the like
Mhm.
made them work in the computer for like not just computed these functions on the computer, not by hand. Actually, this is not so hard by hand also.
Well, for small examples.
Yeah. Okay, so this is maybe like one can ask what now. Here are some generalization of this. So let us start by generalizing the number of words. So 2 is nice, but we can look at many words. And actually, we don't have to focus only on words. We can also go to subgroups. In our method, only finitely generated subgroups. So, what does it mean? So, say we draw a uniformly random homomorphism alpha from the free group F to the finite group G, and apply it on every free subgroup H1 up to HK. the cyclic case is what we discussed before. So now we get random subgroups of the finite group G, okay, which have like some common probability space. And we say that the subgroups are freely separated if there is some basis of the free group for which they share no letters, or equivalently there is a free decomposition of the free group to free factors such that each subgroup contains in another factor. And then one can also generalize the separation rank. Really verbatim, just take the minimal rank of a subgroup containing all these subgroups, and such that the subgroups are not freely separated in J. And all the equivalence before just keeps being true. So these subgroups are freely separated if and only if they give independent random subgroups of every finite group G, if and only if. Now we have something which is a weird generalization of the unnormalized correlation. So it is the probability of the intersection minus the product of the probabilities, which may be not like a standard way of measuring correlation, but this is what we need here. And then this correlation just has this formula, which is n to the minus separation rank of these subgroups times the number of critical subgroups getting this minimum plus very small error. And as Tomer already asked, there is an algorithm to compute this. Now let us look at a very similar question that I find maybe attractive for other reasons. So in some cases we don't want words but conjugacy classes of words. For example, if the measurements that we take on our finite groups are conjugacy invariant. In this case, of course, one cannot separate two conjugated words. So it turns out that we still can, this is still profinite, in the sense that, or profinitely rigid, in the sense that we can still recognize separation of conjugacy classes also using finite groups, and it turns out even to be easier than the previous case. So the following are equivalent. There is the composition of the free group such that each word can be conjugated into one of its factors. And secondly, the classes, the conjugacy classes in a finite group are as random variables taking values in conjugacy classes are independent. 3, if we take specifically the symmetric groups and just count the number of fixed points of every word, then these random variables, the number of fixed points, are uncorrelated for all n, or for the correlation is non-positive for infinitely many n. So stating it the other direction, we claim that if the words are not conjugated, freely separated ones, then for large enough n, we have positive correlation. Also, this can be generalized to subgroups. So if we have a subgroup of the free group, let us denote by fix of it the common fixed points. So for example, for Sn we have 0 because there is no common fixed point of all Sn. And one can also generalize covariance of random variables to be the expectation of the product minus the product of expectations. And then we can just state, yes?
No, what's expectation of what? I mean,
So for any random variables, you can look at this quantity, and in a second, we will see.
but
Yes.
no, I mean, weren't we looking at group valued?
So we will look at the number of common fixed points of these
Okay, right.
subgroups.
So you get something numerical. Okay.
Yeah, everything is really computational. So one can look at the conjugacy version of the separation rank, which is just go both over all subgroups containing, subgroups of the free group, but not containing the words, but conjugates of the words, and then minimize this rank, and or take the critical subgroups of this this set, and then one can measure the covariance or the generalized covariance if we have more than two random variables of the number of fixed points of these subgroups, and we have this this formula, which also gives us the qualitative conclusion about they are conjugate to freely separation, if and only if they are if and only if you can see it in every and just to make sure that we didn't do the same thing twice, then consider these two words, xy x inverse and yxy inverse. So they are conjugate to x and y, which are freely separated, but you can compute the correlation and see that it is positive. So these are really different questions. Now, the context of this story is a very influential paper of Puder and Parzanchevski from quite some years now, and it was maybe a one-word version. I don't know how much the analogy of the result carries on, but surely the proof uses the same tools. So the following, this is a theorem of Puder Parzanchevski. The following are equivalent. W is part of some basis of a free group. The random homomorphism from the free group to a finite group maps it to a uniform random variable. If you look specifically at the symmetric group and count the number of fixed points, then you have exactly one on expectation. This is just proof for a random permutation. And lastly, the number of fixed points on average is at most one for infinitely many n. And also here, the implication from 1 to 2 to 3 to 4 and easy is, and from 4 to 1, it comes from the quantitative version, which computes exactly the leading terms of the fixed points expectation. So one here looks at the minimal rank of a subgroup containing the word such that W is not primitive in that subgroup, and also takes the set of minimizing rank subgroups, and then have this formula.
So why did the n is enough?
Yes.
So if for some point you can show that.
If n is much larger than W, yes. Also in our it uses the same tool. So I will not explain these tools because my time is over. So thank you. Any questions?
Can you put in the last slide one as someone else? Not
Slide that you didn't show.
Thank you.
Okay, if this is a question I can I can answer maybe. Okay, I just say really quick about the proof. So already in Puder Parzanchevski work, what they did is they had this word W, and there were many subgroups containing it. Okay, so these are inclusions. The arrows here are inclusions of subgroups, and then they showed that one can compute the expectation using a sum of functions over the sum over the subgroups containing the word of some function of this subgroup. And this function is actually very close to n to the power of the Euler characteristic, 1 minus the And what they showed, which is highly non-trivial, is that you can have these functions such that from here to itself you get one. I'm talking now about Puder Parzanchevski work, and then you get the result because.
What do you mean from here to itself?
What?
What do you mean from here to itself?
The inclusion of the cyclic subgroup in itself has also an
That's the
associated function.
contribution of one.
Yes. So what we did is looking at. So this is Puder Parzanchevski, and what we did is looking separately, say at the two words W1 and W2, and the subgroup generated by W1 and W2, and you can consider subgroups here and subgroups here, and we found a matching between the two such that they have the same contribution, and the subgroups which are not matched shows the non-separation.
What is the difference between the right and the left?
So you move to the language of graphs, and here you have disconnected graphs and also connected
No,
graphs.
about W1 and W2.
Sorry?
Subgroup generated
This is
by
a subgroup generated by the both, and
So
and here, yeah, I don't want to get into the details. Just a presentation.
can I just say something?
Yeah, sure.
So the left side corresponds to the number of joint. So the probability that both W1 and W2 stabilize the n, the equivalent n. And the right side it corresponds to the product of the two probabilities that each word stabilizes the n.
Up to a factor of n.
Yeah.
Yeah, there is actually of by one in the sonnet. Yes.
So you mentioned this algorithm. To compute the probability rank, we don't have 29 time algorithm. So why is it easier? Yeah.
It's not easier. It is the same. It is the same algorithm. It just I set to the number of letters in the exponent, and this is the rest.
the parameters, I think.
Number of letters of the three group, not of the word.
Yes.
Yeah.
Okay.
Yes, this is a very delicate.
Would you like to ask some questions about Lubotzky? For example, you showed that Sn is the worst case, maybe some cases are better. What about these type of hypotheses?
This is very interesting. Well, for a billion groups, I know the answer, but like in general, there are lots of groups.
So you can imagine doing it over, I don't know, SLNF P, taking P and doing some
I'm sure
linear algebra.
I swear that it must be true, but I don't know.
It must be quite bad if you fix P and let N goes to
Yes,
P.
yes.
Yeah. But we don't have the basic result is still
Fix
not known.
N and let P goes to P.
We don't have the probability rank result there. The full computer.
Yeah, but I'm sure like we will have. You will have. I don't know. Like someday. I'm sure it's true, but yeah, I'm
No, actually, I would guess that if you take SN2P,
That fixed the rank.
quite likely that maybe the result is not correct.
Mhm.
It might be interesting.
yeah.
You think it's not?
Maybe it's not hard to. I think about it. To maybe to find it from.
Simply there are some elements which are unexpectedly conjugate.
Yeah, that makes sense. Yeah, you have two words that are not conjugated. That give you the same solution.
Every representation works. But it's not the same thing.
Let's thank Yotam again.